Let's begin a new chapter in our study of thermodynamics. In this one, we're going to use properties taken from tables to find states of thermodynamic substances. Now, this first one of three problems is rather long, and so I've broken it down into three parts: 3.01a, 3.01b, and 3.01c. Let's look at how we can determine the phase of a substance given its pressure and temperature. Well, to introduce this, I'd like to introduce what we call a temperature TV diagram. So it's temperature plotted against specific volume, and a PV diagram is pressure plotted against specific volume, both 2D plots. And each of these diagrams has what we call a vapor dome. So this is the vapor dome on the TV diagram. It's just a big dome, looks something like this, and we have the same dome on a PV diagram. At the very top of the vapor dome is the critical point, which we will talk about shortly. Now, there are three different phases indicated on this diagram. On the left side of the vapor dome, it's called a compressed liquid. I prefer to call it a subcooled liquid. Underneath the vapor dome, in this area here, we have a saturated liquid vapor mixture. So it's a mixture of saturated liquid and saturated vapor. And that could be anywhere from here to here, anywhere under the vapor dome. And I just like to call that a saturated mixture. Then on the right side of the vapor dome, this is superheated vapor. So those are our three phases: subcooled liquid, saturated mixture, and superheated vapor. Now, if on the left side of the vapor dome here, if it's on this line, it's pure saturated liquid. There's no saturated vapor. And if it were on this line, it's a saturated vapor. There's no saturated liquid. But anything in between these, underneath the vapor dome, in between these two lines, including the two lines, we have a saturated mixture. Now, let's plot a constant pressure line on this TV diagram. A constant pressure line goes up to the right on a TV diagram, but is always horizontal under the vapor dome, and then up to the right. On a PV diagram, we would have a constant temperature line. And constant temperature lines go down to the right, but are always horizontal underneath the vapor dome, and then they continue down to the right. Okay, so we basically at this point know that we need to identify, given a given state at some pressure and temperature, we want to know whether it's a subcooled liquid, a saturated mixture, or a superheated vapor. And we can do this simply by looking in the saturation tables. So for every substance, and we'll use water in this example, there are two saturation tables. One is organized by pressure, and one is organized by temperature. Now they have exactly the same data in them. They're organized this way for convenience. It might be more convenient for me in one situation to use the saturation table organized by pressure, and at another time it might be more convenient to use the saturation table organized by temperature. Okay. So in the first case, so we'll go to the saturation table, and we want to find out which one of these three phases our state exists. Now, if we look in the temperature table at the substance's temperature, and we find that its pressure is equal to the saturation pressure listed in the table, then we know it's a saturated mixture. That means it's somewhere under the vapor dome. Or if we look in the pressure table and we find that the substance's temperature is equal to the saturation temperature listed in the table, then we also know that it's a saturated mixture. Okay, so that's the easy one. All right. But what if neither of these is true? What if we look in the pressure table and we find that the substance's temperature is greater than the saturation temperature? Okay. In that case, it's a superheated vapor. Or if we look in the temperature table and we find that the substance's pressure is less than the saturation pressure listed in the table, then that also is a superheated vapor. And finally, if we look in the pressure table and we find that the temperature of our substance is less than the saturated temperature, then it's a subcooled liquid. Likewise, if we look in the temperature table and we find that the substance's pressure is greater than the saturation pressure, then that is also a subcooled liquid. Now this seems a little complicated at first, but we have various ways of getting this in our head so that we can just look in the saturation table and very quickly determine which one of these three phases we have. All right. Now the way I do this, I mean, obviously this first one's pretty straightforward. If you look in the saturation table and find that your substance is at the saturation temperature and saturation pressure, well then you've got a saturated mixture. But what if it's not? How do we remember this rule about it being superheated or these rules about it being subcooled? Well, I have a mental model that I use. You may find it useful or you may develop your own. But I think of a sphere of saturated mixture. Okay, and anything that is going to expand this sphere is going to flash this mixture into vapor. Likewise, if I have this imaginary sphere of saturated mixture and anything that is going to contract it is going to squeeze it down into a subcooled liquid. So that's my mental model. Well, let's apply it. So I'm going to start with my imaginary sphere of saturated mixture. And let's say that I find the temperature of the substance is greater than the saturated temperature. Well, a higher temperature is going to expand my sphere and flash the mixture into a vapor. So that higher temperature tells me it's a superheated vapor. Likewise, if I'm looking at pressure and I find the pressure is less than the saturated pressure, that lower pressure will also expand my imaginary sphere of saturated mixture, and that will also flash it into vapor. And so I know that if either one of these things is true, my imaginary sphere expands into superheated vapor. Now, on the other hand, I'll start with my imaginary sphere of saturated mixture, and I find that the temperature is less than the saturated temperature. Well, the colder temperature is going to shrink it. It's going to contract it, and that's going to contract it in my mind into a subcooled liquid. Likewise, if the pressure is higher than the saturated pressure, that will also contract my imaginary sphere and squeeze it down into a subcooled liquid. So that's how I do it. You might come up with something better for yourself, but I find that I don't really have to memorize this. I just have my little model. And whenever I look in a saturated table, it's very easy for me to determine whether the phase is saturated mixture, a superheated vapor, or a subcooled liquid. Let's do a problem to illustrate what we just talked about. I have some water at two different states. Let's look at the first one. The pressure is 0.47 bar, and the temperature is 45 degrees C, and I want to determine what state it's in. So I'm going to look in the saturated water table. Now, I'm not going to find a pressure in the table of 0.47 bar, but I will find a temperature of 45 degrees C. So I'm going to go to the saturated water table, which is organized by temperature, and I'm going to come down here to 45 degrees C, and I'm going to find the saturation pressure. And we find that the saturation pressure is 0.096 bar. Well, is this state at 0.096 bar? If it were, it would be a saturated mixture. But no, it's at a pressure of 0.47 bar. So the pressure is higher than the saturation pressure. And by the rules we developed on the previous slide, this higher pressure causes it to be a subcooled liquid. Let's look at another problem. I have water at a state of 30 psi and a temperature of 272 degrees Fahrenheit. I'm not going to find 272 degrees Fahrenheit in the table, but I will find 30 psi. So I'm going to go to the saturated water table in English units, and I'm going to get the one that's organized by pressure. And I'm going to come down here and find a pressure of 30 psi. And at that pressure, the saturated temperature is 250.34. Is our temperature 250.34? No, it's higher than that. And because the temperature is higher than the saturated temperature, then I know that I have a superheated vapor. Let's solve another problem. We're given that water is 140 degrees C and that its specific volume is 0.5 cubic meters per kilogram. So these two independent properties define the state. Notice that we're not given temperature and pressure this time. So we want to find out what phase this state exists and also what the pressure is. And we want to plot it on a TV diagram. So as always, let's begin in the water saturation table. And I'm going to use the temperature table because I know that it's 140 degrees C. So I can come down the saturation table to the 140 degree C row. And the first thing I see is that the saturation pressure at this temperature is 3.613 bar. So right now, let's just go ahead and draw these the temperature and the pressure line on our TV diagram. So we've got temperature versus specific volume and have the vapor dome. And I'm going to lay a horizontal line right across this vapor dome, and that's going to represent a temperature of 140 degrees C. Now the saturation pressure at 140 degrees C, as we saw, was 3.613 bar. So let's put that pressure line in. Remember, on a TV diagram, a constant pressure line goes up to the right, and it's always horizontal underneath the vapor dome. And so this pressure line is going to lie, at least this horizontal section will, it's going to lie right on top of this 140 degrees C line, because at 140 degrees C, 3.613 bar is the saturation pressure associated with the temperature. So the question now is, where does this state lie on this 140 degrees C line? Well, it might be to the left of the vapor dome. It might be under the vapor dome. It might be to the right of the vapor dome. So what we have is the specific volume is given. So let's compare the specific volume to V sub F and V sub G. Now V sub F is the specific volume of a saturated liquid at this temperature and pressure. And V sub G is the specific volume of the saturated vapor at this temperature and pressure. And we know that this state exists at 0.5 cubic meters. Let's look up V sub F. So we have a column here called specific volume, and we have the specific volume of the saturated liquid. And notice that it says it's the saturated liquid times 10 to the third. Or down here it says that the actual value is the table value divided by 1,000. So they're doing this to save table space. So we see that V sub F is 1.0797, but I have to divide that by 1,000. So V sub F at this state is 0.0010797. And we see that V sub G is 0.5089, so that would be this point right here, 0.5089. Now, the specific volume that's given for this state is 0.5 cubic meters per kilogram. That lies in between V sub F and V sub G. It's closer to V sub G, so I'm going to plot it here on this TV diagram. This is the location of the state. And we can see that it is a saturated mixture, and there is more vapor in it than liquid, but it's a saturated mixture nonetheless.